Okay. So first of all, I had a little mess up yesterday. I forgot about office hours. They somehow got moved off my calendar from a repeating event. So anyway, I apologize about that. It's completely my fault. So because of this, we're going to make up office hours today. So for the people that were there, I apologize. And we're going to hold them today. I said in the email we're going to hold them also on Wednesday again from 2 to 3. But realize that actually might not be as helpful as it could be. The homework's due next Tuesday. And I imagine if you come today, you might make more progress by Friday rather than just by Wednesday. So we'll hold them instead today and Friday from 2 to 3. And then again on next Monday from 2. And then usually the ones before homework is due will go longer. So we don't stop at 3 exactly. We can keep going until people, within reason, until people run out of questions. So today, Friday, and then next Monday as well. And then they'll keep up next Monday, and it won't happen again. Were there any questions before I start about sort of higher levels of the homework? I mean, any specific stuff we can ask about this, but has everyone at least taken a look at it? It's been out for a week now? Yeah?
For the questions with coding, would you
yes.
prefer to have the code embedded in the response to each answer or separately?
It doesn't really, you can do either, however you want. It's a little easier for me if I can see it with each answer. And so actually for coding, I think the syllabus says this and the homework says this, I believe. But for coding problems, just turn in a printout of the code. That can be either stapled, put all your code in the back, stapled to everything if it's just easier for you to print it out that way. Or you can embed it in the answers if you want. If you're writing it by hand, sometimes it's harder for people to then embed code in writing. But if you're typing it out anyway, then you might as well just embed it in the typing. Yes, you're welcome to do either whichever you see fit there. But I think you can decide. It's a little easier for me if I can just parse it as I go. But in all cases, hand in a printout of your code as well as the results that your code gets. So if your code gets a numerical result, tell me that numerical result. It can be as text as a MATLAB command prompt. This is what the answer it got. If you ask for a figure, then print out those figures. Don't assume that I can parse the code and guess what the results are without seeing the results. So doesn't matter if it's at the beginning or the end, but please do hand in both the actual code itself and the results you get from that code. Those things are both very important for evaluating the problems. Any other general questions? Okay, and I hope to see people today, if not yesterday. All right, so today we're going to keep talking about classification. And we're going to talk about classification. What we talked about last time was support vector machines and how support vector machines are really the same thing as this loss function plus regularization term that we saw in regression. It's just a slightly different loss function we have, right? Instead of this squared loss, it's, in the case of support vector machines, this hinge loss function. Or for logistic regression, it's this logistic loss function. What we're going to do today is finish up classification. In particular, I'm going to talk about this logistic regression function here and talk about how we use Newton's method to minimize logistic loss. Because unlike squared loss, for example, we don't have a closed form solution for that. So we need to use some iterative procedure to actually optimize that. I'll then briefly talk about nonlinear classification. And this is actually going to be a pretty short topic here, because the nice thing about using this same exact framework for classification as for regression is that all the same rules apply, right? So we can do the exact same tricks as before, namely explicitly explicitly using nonlinear features, right? Taking our feature function and just using nonlinear features of the data instead of just linear features. That will give us a nonlinear classifier. Or we can use kernels too, right? We use the kernel trick, write the data vector as some sum of the feature vectors, and this works the exact same way. There's really no difference in nonlinear classification once you've done it for the regression case. So it's really not that much to say. I can show you some examples of what it looks like in terms of the decision boundaries that it gets. But really, this is the same kind of stuff we were doing before. And then finally, we'll get to the last topic in machine learning, which is about evaluating machine learning algorithms. So far, I've been talking really about how do you minimize loss. And I've talked about things like overfitting and these kind of things in very generic terms, right? So I said, this looks like it kind of overfits the data. This looks like it's going through these points too much, but it won't perform well on nearby points. So I'm going to define this a bit more rigorously then. And this not only has to do with sort of picking the best parameters for a machine learning algorithm, this also relates to how we would go about actually reporting how well these algorithms actually perform. So if you want to write a paper about these things, how do you actually say, well, we got this good performance on this task? And is that good? If you say a number like 0.2, well, is that good or is it not good? I don't know. So how do we go about reporting the performance of machine learning methods? And that's what we'll finish up talking about today. Probably won't get through all that today, but we'll at least get started on that. Were there any questions from last time? Last time I started talking about Newton's method, and I'll recap the multivariate case, but I'm not going to recap the single variable case. So were there any questions about Newton's method from last time? I also realized that the video from last time, the classification video, didn't go up, so I posted it this morning, but it takes a little while for YouTube to process it, so it should be up today if you want to go through that again. Sometimes these uploads just get kind of corrupted. I'm not quite sure why, but they're big files. All right, so the high level here is that for logistic regression, we have some cost function we're trying to minimize. So g of theta here equals the sum from I equals 1 to m of, in this case, the log of 1 plus the exponent of yi times theta transpose phi xi. Okay, negative here. All right, so this is our loss function for logistic regression. And the high level of this all is that we can write the gradient. I'll actually just tell you the next slide what it is. I won't go through deriving it, but we can write the gradient with respect to theta of this cost function. This will equal something that we'll see here. And this is, by the way, going to be a vector, right, in r to the k, because theta is k-dimensional. This is this is a real valued function, and the gradient of a real valued function is just going to be a vector that's the same size as the input, because each element, right, is just the corresponding derivative. So this is something. I'll tell you what it is in a second. But unlike, and what we did with least squares was we just took this thing and we set it equal to 0, and then we solved for theta. But it turns out that for logistic regression, you can't do that. This is of a form where there's actually a lot of thetas kind of in a nonlinear way here. They enter into this. I mean, you can imagine, right, you have logs, exponents. These make theta enter into the equation in different ways, where it's not possible to just write down an expression for what theta actually is. I mean, there's exponents and logs of theta, and you can't just exponents actually. But there's terms in theta that you can't solve for analytically. It's sort of a nonlinear set of equations in theta. And so what we're going to do instead is iteratively find a procedure that makes this thing 0. So we want to find a point where this is 0. That's going to be the minimum of our function. Remember, there was also some discussion of, is this a minimum or a maximum, that kind of stuff. This ends up being much like least squares, a convex function. So any point where this is 0 is actually the global minimum or a global minimum of this function. So we want to find some place where this is 0. That's the best set of parameters. That's the parameters that minimize our cost function here. But we need some way of actually doing this, finding some theta such that this thing equals 0. And the reason why I introduced Newton's method is a general algorithm for finding zeros of some function f. So Newton's method says if we have any function f, if we have any function f that takes as input vectors in Rn and maps to vectors in Rn, then we can find some x such that f of x equals 0, we can do this by first starting at some initial point. Say take x being 0 for the first point, or something like that. You can take some other points within reason. As I said before, Newton's method can sometimes diverge, so you want to be careful about picking too crazy points. But for logistic regression, at least, it will typically converge if you pick a reasonably sized initial value. So for Newton's method, we want to find some x f of x equals 0 for any function x, any function f. And the way we do this, well, actually, I used z before just to not confuse with these x's here. So let me just write z here. F of z equals 0. And the way we do this is we repeat the following update. We keep setting z to be equal to z minus the Jacobian with respect to z of f of z, inverse times f of z. And what this is really doing is this is forming a linear approximation to that function. Setting that linear finding the z that makes that linear function, that linear approximation equal to 0, and then setting z to that new value. It's a little easier to see in the single variate case, but the multivariate case is exactly the same. It's doing the exact same thing here. Now, the way this ties into this problem, finding a theta that makes the gradient of this cost 0, is, of course, we're going to have this function here just be the gradient. Okay, so we're going to find some theta such that this whole thing, really you can think here of effectively f of theta is equal to this whole thing here, the gradient of that, right? That's the right size because that takes as input the parameters and it outputs a vector. So input is in Rk, the output is a vector in Rk, and we want to find something that makes this function 0. And that's what we're going to do. Now, we actually even have a name for this. So now let me, I've first written the method in the general form here. Now let me write it in the case where f is of this particular form. I mean, I could just leave it, actually. In fact, this is all entirely right, but let's just specialize it a little bit. So now we have Newton's method for finding a 0 of this gradient term. And in fact, there's actually a special name for this. So you remember when we talked about matrix calculus in that quick review of linear algebra and calculus, that the Jacobian of the gradient was another term. This is analogous to the second derivative of a function. And this is called the Hessian. So the Hessian, remember, is a, well, let me actually just erase that. So remember, the Hessian is a matrix, so we write it like this. Hessian with respect to theta squared, f of theta. Well, all right, I'm going to write it for switching between the general notation here and the notation for this case. But the Hessian of z with respect to z is a matrix. First of all, it's a matrix in R. Let's see, I'm saying there it's a function from f of n to R. So this would be an n by n matrix, where the ij element here, the ij element of this is going to be the partial derivative, the second partial derivative with respect to f with respect to zi and zj. So we differentiate with respect to zi and zj. By the way, I and j can be the same thing. So the diagonal terms will have sort of, you differentiate with respect to zi twice, say, on the diagonal entries. And the ij elements of this matrix are given by this. So basically, it's the matrix of all possible second derivatives we have of our function here. Okay, and importantly, this is just, remember, the Jacobian of the gradient. So Newton's method worked with the Jacobian of the function, and the Jacobian of the gradient is just this Hessian term. So it's just a little more convenient to write it in terms of this because it kind of emphasizes what all these terms actually are in terms of their first or second derivatives. So what the Newton update for this function becomes then is the following. I'm going to erase this. It's up there too. So this is just, I'm just copying what I wrote there because I want to write sort of the actual Newton's update for this case. So remember, Newton's method becomes this. So let's say, the generic here would be z going to z minus this Jacobian term of z inverse f of z. When f is this gradient term, though, and I'll even write theta here, so, let's see, so minimizing j of theta, what this update would be is it says, OK, well, we're changing our theta parameters, so we're just going to set theta. Theta is our input to the function here. Theta is set to theta minus this Jacobian term, but it's the Jacobian of the gradient, which is the Hessian. So we're going to take our Hessian term here, the Hessian with respect to theta of j of theta, times our f term here, which in this case is just the gradient itself. So this inverse times the gradient, j of theta. OK, so that's our Newton's method update for finding a theta such that the gradient at that point is equal to 0, i.e. finding a value of theta that minimizes this function j. OK, so does that sort of conceptually make sense to everyone? What's going on there with this Newton's method for this case here? I believe one of the homework problems, not in this homework, but in the next one, will also ask you what the Newton update would be for least squares. So think about that a little bit. Question you can ponder for a little bit. Not in this homework, though. OK, so we have our update. I guess I'm switching between generic and specific forms here. But this is the update we use to find a minimizing point for something we can't analytically solve for, like logistic loss up there. OK, so now, of course, to actually apply this to the logistic loss, we need to know for this function, well, what are the gradient and the Hessian? And rather than actually do this too much, I'm just going to go ahead and say it's those things. These are the gradient and the Hessian. Let me actually describe a little bit how you get that. So basically, I'm saying that the gradient j of theta equals negative phi, that's our same phi matrix as before, transpose this matrix z times theta, where z is a diagonal matrix that has these entries. So we're basically taking z here is going to be m by m. Z is an m by m matrix diagonal. So basically, z is scaling, say, the entries of y. Multiplying on the right by diagonal would scale all the entries of y. So we take all of the y, element y's, scale them by this amount here, and then we multiply by phi transpose. So where does this come from? And I'm not going to go into too much rigor here, because it's not really the point of the class to test your calculus knowledge. It comes basically from basic calculus. So if you take element y's derivatives here. So let's take the element y's derivative with respect to theta I. Actually, let's not use I, because I'm summing from I there. Theta j here. Of j of theta. Well, that would be equal to, first of all, we can just move the derivative inside the sum here. So that's the sum from I equals 1 to m of the derivative, partial derivative with the theta j of log of 1 plus exponent negative yi times theta goes phi xi. OK. Now we use some basic rules of calculus to say when we take a derivative of a log that puts 1 over this term outside, then we take the derivative of what's inside here. So this will equal the sum from I equals 1 to m of 1 over this thing, 1 plus x negative yi theta transpose phi of xi times the derivative with respect to theta j of this thing. Well, this goes away. This would just also bring out one term like this. So we're also going to have an exp of negative yi times theta transpose phi xi. And then finally times the derivative with respect to theta j of this thing, which in this case would be times yi negative, I'll just put negative here, negative yi phi j xi. Okay, so does that everyone at least follow what I was doing there? I was just applying the chain rule essentially to differentiate with all of these things. And then I'm going to use this little property here that for this thing, let's see, so negative exp of, let's say, negative z over 1 plus exp of negative z. We're going to just factor away one of these things. And I believe this equals also, I did my math right, could have made a mistake, exp of z, right? Does everyone agree with that? Because you basically can multiply the top and the bottom by exp. Let's see, you multiply the top and the bottom by exp of z. This cancels out to be 1. This would be exp of z. This would be 1. Do I have a negative there? Yes, negative. Right, it's negative 1 over that thing. OK, so now we have this being the basically 1 over this thing times yi times phi of xi. And if you use some of our rules of matrix notation here and put this into matrix form, what you'll find is this, all the elements here end up being sort of this vector we have of all, the matrix we have of all the phis times this diagonal term, where this diagonal term is capturing this guy right here, and then times the yi. So that's where everything comes from. But you can verify that if you want to. You can check that to make sure it's correct. So again, I'm not going to go too much into that because I think that's not the point of this course, to get you able to do that kind of stuff. But just if you can, as long as you can see where it comes from, and if you spent the time, you could derive this yourself. That's sort of good enough for this class. Okay. All right. So and then you'll also trust me here that if you do this again and differentiate twice. And you have to just do it. I mean, you have to just take all these terms and put this thing is now in the denominator, you have to square that and cancel terms out, etc. If you do that twice, then what you'll find is you'll find this. You get this expression here. And so that's actually looks surprisingly like the gradient in Hessian for linear regression, just with these extra z terms in there, kind of interestingly. That's not a coincidence, but we won't worry about that connection too much. Just the neat thing to note if it's obvious. Okay, so here are the gradient in Hessian. And for the purposes of this course, we're just going to say, okay, that's that. They're the right size, right? Because this should be a vector in Rk, right? So let me see this term here. Well, big phi is m by k, so phi transpose would be k by m. Z here would be m by m, and theta here would be, sorry, I wrote theta. I meant to write y. Yeah, don't want to make that mistake. Y is m by 1. And so this whole thing is going to be k by 1. That's right, that's the right size. Similarly, this one, you'll see it's going to be k by k, which is also the right size that we want. So everything kind of checks out in terms of the sizes. This update will give us a way of updating our parameters theta, which is the right size. So now what we're going to do is we're just going to follow that thing exactly. Our updates will be, I'm going to erase that because it isn't really important that you have that stuff down. Our updates will be theta. We set it to the current value of theta minus this thing, phi transpose z, z I minus z, phi inverse times phi, actually it's plus, right? Because we have a a minus on the gradient there, times phi transpose z y. And we just repeat that again and again until the theta stop changing. We could also, so actually this is an interesting question. How do you decide when to stop Newton's update? Right? You're running this update, you're computing the update, and you keep getting updates to theta. I told you before, remember, that Newton's update converges really fast once it's close to the solution. So you actually, the number of correct decimal points you have in your solution will double at each time step. So very quickly you will reach the precision that a machine is capable of representing. And so there will not be any value in repeating that again. And typically people choose how to stop in one of two ways. You either look at how much theta is changing from iteration to iteration. When it stops changing very much, then you stop. Or maybe a little bit more directly, because ultimately we want the point where this gradient is equal to 0. You're computing the gradient as you do this, right? So you just measure the norm of the gradient, and when it's less than, say, 10 to the negative 12 or something like that, you stop. That's sort of a little bit more common way of doing it. Let's look at some code that does this now. And this is a function which I don't think I ask you to use this in the homework, but you can try it out maybe for the project or anything else if you want to apply these methods like a support vector machine or logistic regression to a problem. You can try this. So what we're doing here is, this is the function. It takes as input our least squares that will take as input the feature vectors and the true outputs. In this case, though, the output is +1 or -1. We just do some initialization at first. So theta we set to be 0 at first. G is the gradient. We're just setting it to be 1, even though it's the wrong size. That's just for the stopping conditions. And then we repeat, and as long as the norm of G is greater than 10 to the -10, we're going to keep updating it with this Newton's method. Okay, so that's our stopping condition for gradient descent. For Newton's method for logistic regression here. We're going to wait until the gradient's norm is less. Once it's less than 10 to the -10, we're going to stop. Okay. On the first one, I'm computing the diagonal elements of that Z matrix. So what I'm doing there is I'm computing all the elements along that diagonal. I'm storing as a vector small z rather than matrix Z because there's no real point in storing that great big matrix. But this is what I'm doing in the first step. Then I form the gradient here. Boy, it's really hard to point this thing. I'm going to form the gradient here. This is just our formula. I'm using, instead of big Z times Y, remember, a diagonal matrix will just scale the entries of Y. So I'm just writing little z dot times Y. That's the same thing in MATLAB speak as big Z times Y in linear algebra speak. So form this, the gradient, then form the Hessian. You can actually do this. I'm just writing the diagonal matrix here explicitly. You can do this more efficiently with some other functions, but we won't worry about that here. You have to basically use a function that will scale every row of that matrix by the same thing. But we'll just form a diagonal matrix here. And then I'm setting theta to be equal to theta minus h backslash g, which is h inverse times g. Okay, and then I repeat this process. And that will, in the end, output a theta that actually solves this problem. So why, again, a while back, I also wrote some code for this, which you might remember. It is this code, right, where we just wrote in YALMIP, solve the sum of the logs of 1 plus exponent of that thing. That's exactly what we want to minimize, right? And YALMIP lets us actually write that down really succinctly, and so we can do that. So this is also code here for logistic regression. So why on earth would I want to go through all this pain of Newton's method and all this kind of stuff? Well, first of all, actually that might not even work depending on your solver. I think Sadumi does a really bad job of this one. You have to get a better solver to actually solve that code there. So it's tricky. Things like the log and x are actually tricky for things like YALMIP to handle. They only work some of the time, but it works sometimes. But even when it works, for 300 examples and 3 inputs, I guess I should say k equals 3 here, not n equals 3. But for m equals 100, so 100 examples and 3 features, this took about 20 seconds to solve with YAML, and it takes 16 milliseconds or so with logistic regression. That actually can be sped up a lot. If you make this diagonal multiply here a little more efficient, it'll be on the order of a millisecond or so to solve this. So that's why. I mean, we're talking about a very, very big difference in time here. It's similar to how much longer it would take YAML to solve linear regression. If you write minimize some squared error term, that's much, much slower than saying phi/y. Many orders of magnitude slower. And similarly, YAML appears going to be many orders of magnitude slower than just the specialized Newton's method code. By the way, this is also true for support vector machines. So in this class, you're going to write a support vector machine. That's great. You should be proud that you can write a support vector machine. I mean, you don't do that in a lot of machine learning courses. But with the big caveat that if you actually were to get a big data set and try to apply YAML to solve it with your support vector machine, this is going to be pretty slow. You're going to max out at maybe 1,000 examples you can process or something like that. Whereas there are lots of libraries for support vector machines that are available that are going to be much faster. 2 very well-known ones are called libsvm or svmlite. You can just Google those names and they'll be the first hit, certainly. So if you have a big problem where you want to apply a support vector machine, don't write it in YAML. Write it in YAML at first, with a small amount of data, so you can kind of get an example, an idea of, is this even going to work? Does this have any hope of working? But once you actually, are past the point of just using your little example and want to actually apply it to 5,000 examples or something like that, or even more, just use one of these packages. They're really fast. Or use this if you're using logistic regression. This code is actually pretty good for logistic regression. It's not bad at all. OK, so here, let me now show what this actually looks like, what Newton's method actually looks like. So this is the first iteration of Newton's method. I'm plotting here, remember, the separating hyperplane. So what's really happening here is this phi transpose theta in this. This is our old example, right, of the refrigerator, where we have 2 refrigerators here. This is refrigerator 1, this is refrigerator 2. We're trying to separate, is this device on an outlet we don't know about, this device A or device B. And this is our examples described in terms of the power and in terms of how long they last for, right? So after one iteration of Newton's method, this is the separating hyperplane. And it's kind of OK, but you can kind of imagine, well, this is all right, but we're kind of making a lot of mistakes here that we don't really have to. Maybe these we can never get right, obviously, right? Because they're kind of, at least in this representation, they are completely surrounded by examples of the other types. So you're never going to be able to separate these two things, not with a linear classifier. But like these, you feel like you could sort of do better. And so what Newton's method does actually is that, well, actually, I shouldn't say this interpretation because we're not really covering it like that. But basically, what's happening here is that this is not the actual theta that minimizes logistic loss. It sort of does OK, but it's not minimizing it yet. It still has a positive gradient. And so what we see is that this is the first iteration, but it actually looks OK. I mean, it's sort of all right. Here's the second iteration. So it's kind of pushing the hyperplane to classify these ones a little bit better. Here's the third iteration, and then after 10 iterations, it looks like that. And this is when it's actually converged here. Now, this method here has converged. So, there isn't actually, what's kind of surprising is that there isn't a huge difference. But it is a difference. And we are doing quite a bit better at the objective function, at minimizing this logistic loss after all these iterations than after just one. So here's now what the convergence looks like in terms of measuring the norm of the gradient over iteration numbers. Importantly here, this is a log scale on the y-axis. So we start off, and our gradient's norm is pretty high, right? That's actually sizable, the norm there. Yeah, there's a question?
Sorry, what was your initial condition for the gradient? Was it 1? Is that what it?
The gradient was 0. Well, theta was 0 at first.
Sorry, yeah.
So the g equals 1 there. All I was saying was I'm just basically setting it to some value so it doesn't pass that test. If I set it to 0 at first, it would say you're done, and then theta would be 0 still. So really, what it is I'm not printing that 1. What I'm doing is I'm first evaluating the gradient at theta equals 0. So theta equals 0 gives some gradient, right? I mean, this when z is the thing you get with all the zeros there, gives you some gradient. And so we get a gradient, and that gradient has norm whatever that is, almost 10 to the 5. The actual norm there depends on the scaling of your features and things like this. So don't worry too much about the number. It's the relative magnitude that makes more difference here. So let's talk about some norm. And what's really the thing you should sort of keep in mind here is that how quickly this actually converges, right? So we're plotting, numbers of iterations here, not on a log scale, just in terms of 10 iterations. This starts off at 10 to the 5th and gets down to 10 to the negative 10 after, virtually no time at all as far as a computation goes. Each iteration here is about the same cost as computing a least squares solution, by the way, right? Because you're forming an inverse of a k by k matrix and you're solving for that. So this is like 10 times you're doing least squares, or computationally it's the same cost as doing least squares 10 times, and you found a solution here. So it's not quite as nice as least squares. And actually on the next homework, you'll show an interesting connection between the first Newton step and least squares. But don't worry about that yet. Here, all I'm saying is that let's if we want to actually minimize this thing, we can do it exactly for all practical purposes. I mean, this is, as far as the computer goes, this is pretty much exact. I mean, you could maybe do it one more time and you'd be a little more exact. But this is about as close as you can get on a computer. So we can solve this even though we don't have a closed form for it. OK. So the last thing I want us to talk about is nonlinear classification. Were there any questions about all this first? We're going to say Newton's method again when we talk about power flow. So when we talk about electrical grids and how how power is distributed in an electrical grid, it turns out you have to solve some nonlinear equations again. And we're going to use Newton's method again to solve these. And just like we saw before, what you'll find with those methods is you very quickly get very fast convergence to the solution. So Newton's method is really sort of nice in this regard. It's really, really good at finding these kind of solutions. Again, assuming you start at a good point and you take the right step sizes. But we will always assume that in this course. You don't have to worry about kind of guarding Newton's method for failure cases. OK, so any questions on this? All right. Well, then let's talk very briefly about nonlinear classification. As I said, this is going to be brief because there really is nothing new here. All that we're going to do is we have this exact same considerations. Remember, for linear regression, I guess for nonlinear regression, we talked about two ways you can get nonlinear behavior for your prediction function. First of all, you can explicitly add nonlinear functions of the input as your features. Or secondly, you can not construct them explicitly, but use kernels to implicitly construct these nonlinear functions of your features and work in this high-dimensional space without ever having to actually build them. Now, of course, the punchline is you can do the exact same thing for nonlinear classification. So remember, the trick for nonlinear regression was that we have this yi hat. We're going to still set it to be equal to theta transpose phi of xi. We just make these nonlinear. And the thing that makes this simple for classification is we're using the exact same function for classification. We're not changing. I mean, this was the exact same form for our classification functions. We didn't change it at all. Ultimately, if you want to make a yes/no answer, you just take the sign of this thing. But for all practical purposes, in terms of our loss functions at least, this was still our prediction. It was still predicting a real value, right? And that's why we have these different loss functions, like where the more negative this goes, the worse it thinks it is, and this kind of stuff, like for logistic loss or hinge loss. So we're going to do the exact same thing, and we can just, instead of linear functions of our data here, we just make nonlinear functions. Or instead of writing these explicitly, we just use the same trick where we say theta equals phi transpose times in terms alpha. And this can all be plugged in directly to the other to all the other problems for classification as well. So let's just look at one example. when we talk about kernels. I mean, the explicit features are actually even easier, right? Because then there's just nothing to do. It's just the exact same stuff we saw before. Just we make nonlinear functions of these things. So for features, it's really the exact same thing, though. We're just going to, sorry, for kernels, it's the exact same thing. We're just going to make the substitution. This equals this thing, which is just equal to the sum from I equals 1 to m of alpha I times phi xi. Right? Remember, we could do this whenever we were solving a problem of the form minimize over theta, sum from I equals 1 to m of the loss of theta transpose phi of xi, yi, and then plus some regularization term. So as long as we are problems of this form, we can apply this kernel trick here, and this actually will give us the solution, so we can solve for the alphas instead of this. But the nice thing here is that all our loss functions in the classification were still of this form. They were still of the form, some function of this linear prediction that we have, and linear or nonlinear, whatever, but this inner product here of our parameters, and some function of yi. I mean, before yi was a real number, and you would take the difference. Now you just multiply by it, and so plus 1 minus 1 value, but it's the same thing. There's no difference in terms of this optimization problem. It's still of this form, and so we can still apply the kernel trick as we could before. So let's see then how we might go about getting an SVM into kernel form. So remember, the SVM was in this form. Well, let me just write the objective, I guess, to start with. So let me write the linear SVM. We want to minimize over theta, sum from I equals 1 to m of this function max of 0 and 1 minus yi times theta transpose phi xi. Remember, in MATLAB, the way we wrote that is we said, OK, I'm going to form a vector of all these things here. So this vector here was going to be effectively, I'll write it sort of in linear algebra notation. It's going to be phi times theta. This is a vector of our predictions, and we're going to multiply element-wise by y. So let me write it in MATLAB notation. No, let me write it. Keep being indecisive here. So we're going to write this in linear algebra notation. So it's going to be like a diag of y times this thing. That'll multiply every element of this guy by the corresponding element of y. We will subtract 1 from this. This is now a vector of all ones, because this is a vector. And I'll be patient a little bit and just say max of 0. And this thing is going to be our loss function. And we're going to sum that all up. Where this max is taken to be element-wise, we see if this is bigger than 0 or not. And then we take the sum of all this thing. So say 1 transpose times this whole thing. OK? That's kind of our loss function written in very compact form without a sum. So was that a bit quick for everyone, or does everyone kind of follow, or at least could follow that? We went through this before, right? How you write this all out, kind of term by term, but this might have been a bit quick that I just did that there. Does everyone see how this is the same as this? OK, so now all we do is we just take the exact same thing we did before, right? We just take this instead of theta. We write phi transpose alpha, and we note that this matrix, just like before, phi transpose is just equal to our kernel matrix. That's it. We're done. This is now a kernelized nonlinear SVM. Oh, actually, we also had a regularization term here, I should add. So we also had lambda squared, and that would just be, like before, we'd have alpha transpose k alpha. We saw how that worked before, right? Times lambda. This is our nonlinear SVM now. So the way we write that in MATLAB is just, well, first of all, we times k times alpha. That's all our vector predictions. I'm using the dot times here rather than the diag, because it's just a little easier. Dot times this, 1 minus that, the max of that, and 0, and take the sum. And then you also add this term here. And that's our SVM. So now you actually have to use a kernelized SVM. And kernel SVMs actually, I mean, those are kind of one of the main state-of-the-art algorithms in machine learning, actually. This right here. So this line of code right here is actually, it's not state-of-the-art at this point. There's some better methods that will get you in terms of raw accuracy, but it's pretty powerful. Of course, the art of using SVM and kind of the challenge is the higher level stuff of, how do you pick the kernel, how do you pick the parameters of the kernel, all these other kind of things. But in terms of a raw algorithm, this is actually, amongst the state-of-the-art in machine learning. So that's a nice thing to know about. Okay, any questions with this? I did this kind of fast here. If you weren't following this, come talk to me in office hours or some other time, because it's important to see what I'm doing here. But I had gone through most of the parts in a previous lecture, so I'll just write it like that for now, and we can hopefully go from there. Okay, so now let's just look at, oh, and by the way, it's a little bit trickier, but if you also use logistic regression, then you can just as easily write a Newton update for the alphas. I should do this in two ways. You can either formulate it in terms of the alphas to begin with and then find Newton's method, or you can write out Newton's method and then apply a kernel trick in the Newton's method step and do it that way. Those both work, actually. So those are both kind of cool. But they of course give the same answer. It's a little easier conceptually, I think, to first write it out in terms of the kernel expansion and then derive a Newton update for alpha. So typically a little bit easier to do it that way because you always apply this sort of same trick that theta here. You just plug this in and you end up getting something like that. All right, so let's see what this looks like now. Here, so I forgot to actually mention this problem. Before we talked about a problem where you have two refrigerators, refrigerator 1, refrigerator 2, and they're slightly different, they're different models or whatever. And you want to distinguish when you plug one in, is it this refrigerator 1 or refrigerator 2? So that's the first problem we're sort of thinking about here. The second problem that I'm going to talk about is one where you want to know something a little different. Is it a refrigerator or anything else? Right? So you see you have all the plugs in your house. And you want to identify, is this thing that just came on this refrigerator or not? I'm now plotting in some range of power. Of course, the power goes, there's a lot of things that use a lot more power and things that are on for shorter or long periods of time. But in this scaling of the graph here, you plot all the appliances in the house. What you get is here are a bunch of other devices that were not refrigerators, and here was the refrigerator. So you're not going to get 100% accuracy here. You are going to make a few mistakes because some things, at least under this feature representation, that look very similar to a refrigerator, right? In terms of just how long they were on for and how much power they consume, those look like a refrigerator. So what we're going to do, so we're not going to get 100%, but you can also see that you probably could do okay with this, right? Because, these sort of are all kind of in this range here, and there isn't too much. Maybe down here is kind of tough, and there's a couple over here, but for the most part, you kind of see little islands where if you see some event that happens that looks like that, you're pretty sure that's going to be a refrigerator, right? And sort of everything else is not a refrigerator. The problem with using linear regression for this, or linear classification for this rather, is that you can't really draw a plane through this data and say everything on one side is class 1 and everything on the other side is class 2, because you sort of have stuff that's not refrigerator all around the refrigerator. And so you kind of instead want to kind of select this little island here and say this is the refrigerator and everything else is not. But this is exactly what nonlinear classification can do. So remember, the thing to have in mind is not drawing a nonlinear function. For classification, you're not drawing a linear a line directly in this space, so you can visualize it that way. What you're really doing is drawing a 3D plane through this and saying everything less than 0 is going to be class 1, everything greater than is going to be class 2. And that ends up looking like a line through the data, but you could have like vertical lines too, and stuff like that. There's no problem there. Similarly, your picture should not be, let's draw a nonlinear function and try to separate it that way. Your picture should be, let's draw a three-dimensional function, where the surface here is the 0 plane, for example, and everywhere that where that three-dimensional function is less than 0, we're going to classify it as blue. Where it's greater than 0, we're going to classify it as 1. So you can kind of think of a function that sort of pops out here and then goes negative everywhere else. Now I'm going to draw the lines where that function crosses the axis, and where it's greater than 0, I'll draw it as red, and where it's less than 0, I'll draw it as blue. And so this is what it looks like plotted on top of the data points now. So this is a support vector machine using a Gaussian kernel, how it classifies this space. So the way to interpret this, remember, is that this is really a function here. There is a 3D function that is greater than 0 at the points where it's red and less than 0 where the points where it's blue. And what the prediction it makes then is going to be, it's going to predict +1, or the refrigerator, whenever it's greater than 0, whenever it's in the red area, and -1 elsewhere. Okay? And so that is what you should have in mind when you think about nonlinear classification. It's not about drawing a function to the data, because these things can have loops and they can have circles and all that kind of stuff. It's really about drawing a three-dimensional surface for this data, and then where it's positive, you classify one thing, and where it's negative, you classify as another thing. Does this picture make sense to everyone about what it's doing there? That's the classification boundary, essentially. This is sort of the space, how it divides up space into positive and negative examples. Now, much like regression, classification can also overfit, right? We can actually come up with a function that will fit our data very well, but fit nothing else, not a lot of other things. So remember, for a kernel, and a Gaussian kernel in particular, this was the kernel that looked like this, where k, z, and z prime equals exponent negative z minus z prime squared over 2 sigma squared. This is our bandwidth sigma. So if sigma is very small, then these things will sort of fall off rapidly. It means that we can basically have 2 points that are very close to each other that have very different values of this function. If sigma is big, it means that points that are close to each other all are sort of similar under this mapping, and so we have to have kind of similar values to all of them. And so the picture you should have in mind is that this is what a Gaussian kernel looks like for maybe a reasonable size bandwidth. If you make the bandwidth too small, you'll get something like this instead, where it's clearly kind of overfitting the data now. So we actually do OK in terms of classification here. It makes some weird ones, right? Like where you think, OK, it could probably do that well, but this is what it does. I should add, these points sort of around here are very close to 0, so it could really go either way in a lot of those places. It's basically very unsure because it's only making good predictions sort of right around where it's at, where it's seen data before. So it looks something like this, and that kind of looks sort of OK, but it's clearly overfitting to the data now. They're clearly, this is sort of, if you were to draw a region, where's the red, you wouldn't pick that. You pick something more like this, right? And so what's happening again is that just like those functions that we have for regression that sort of did crazy stuff to fit the data points exactly, this is doing crazy stuff to fit the loss exactly. It's a little sometimes harder to interpret what it's doing because remember, it's not trying to minimize the actual error of these things. We can't minimize the classification error. That's sort of an NP-hard problem. What we have to do instead is minimize this loss function, which is a little bit harder to visualize, but basically it's going through all these hoops, making weird lines here to minimize this loss function. So just like before, the big point, just like before, we can have overfitting from the same things. Too many features, wrong parameters for your feature, not enough regularization. These things all cause overfitting of the classifier. So with that, it's actually a very good segue into our next topic, which is how we go about evaluating machine learning algorithms. Okay. So, up until now, I'm going to erase this because this is sort of old at this point. All right, up until now, I have been somewhat informal when I talk about things like overfitting. I've mentioned this a lot, right? You can overfit to your data. Overfitting or regularization, these kind of things. I described a little bit, but I described them kind of intuitively in terms of your function is good on the data points, but not good close to them, which is sort of something you might want to be good at, but why do we really care about that? In this lecture, I'll talk about a couple things. And the fundamental question is, how do we know, how do we evaluate when an algorithm is achieving good performance with whatever definition of good that we want to use? When is that happening? Now, to answer that, well, I should say there are a couple of reasons we might want to answer that. We might want to know, how do we pick, say, these parameters of our algorithm? How do we pick the regularization parameter, for example? How do we pick what degree polynomial to use in our features? How do we pick these things? Well, we want to pick the one that performs best, right? But how do we evaluate what performs best? And secondly, so that's sort of this question here, how do we pick the best learning algorithm? And secondly, if we're going to write a paper about these things, which hopefully some of you are in your future writing papers about things like this, how do we actually go about and report what the performance is? You get a result like your squared error is 0.2 megawatts squared, I guess. What does that mean? How do you actually report how good that is? Is it good? What's the baseline that you should be comparing to? How confident are you in that prediction? Or is it just, did you evaluate on one example? You have some intuition about how you should be less confident if you have a number of examples you evaluated on versus if you have a larger number. Shouldn't you be more confident in your reporting of this error metric? So we're going to talk about how we actually go about reporting formally the results of a linear of a classification or regression algorithm, and we'll talk about how we can use kind of the same procedure really to tune the parameters. So to start off with, we'll go through both these questions too, but we'll start off with this one because it kind of naturally leads to this one as well. So let's start off with asking the question, how should we pick the best algorithm? How do we know? So far we've been talking about how to pick the best theta, and that we can kind of do analytically, right? We can pick the best theta that minimizes this loss function. But how do we know what features to include? How do we know what regularization parameter to include? These are all questions we haven't really answered. So one possibility, I should say, would just be to do the exact same thing we with theta and use the loss function. So remember, are ultimately trying to minimize this thing. I'll leave out for now. I'll leave out for now the regularization. I'll just talk about the features for now. So sum from I equals 1 to m of theta transpose phi of xi, yi. Okay, so we're minimizing this thing. Maybe we'll add regularization in a second. We could, we're picking the theta that minimizes this thing. Why don't we also just pick the features, say, that minimize this thing, right? That also seems like it could make sense, too. Of course, there's a problem there. And the problem is that adding features will always decrease this function, at least for the optimal theta, right? For the best theta, it will always decrease it. And it's very easy to see this, right? Because don't copy this down. I'll put a question mark there, because that's not what we want to do. It's very easy to see this, right? Because if you have some theta that achieves some objective value, and you add another feature, Well, the same exact theta with a weight of 0 on that new feature will achieve the exact same objective value. And it could be, in fact it will be, typically, that by playing around a little bit more with theta, you can get it down even lower, the loss even lower, the sum of losses. At least can't increase it, possibly, right? So I guess I should really not say always decrease. I should say will never increase the loss. It could say it's the same, but it will never increase the loss, and it will, in a lot of cases, decrease it. And the extreme example here is, think about linear regression when the number of features you have is the same as the number of examples you have. So we have m equals k. It turns out there, and this code shows it, but I'll also describe it in a second mathematically, that you will always be able to obtain 0 loss, as long as your features are not dependent on each other. If you actually have m independent features, you can always attain 0 loss. And that's pretty easy to show just from linear algebra, actually. So remember, our least squares solution was, so the setting here is we have phi is going to be m by k. And what if k is equal to m? In fact, k can also be greater than m too. That means we have more examples than features. In this case, I'll just have it be equal to it there, though. Remember, theta is equal to phi transpose phi inverse phi transpose y. So our optimal theta. And then our prediction is going to be y hat equals phi times theta. OK? So remember, in general, this was very important that you don't try to distribute this inverse into this thing, because these matrices here are not square. They are not invertible individually. But if k equals them, these both are square. So we actually can invert each of them individually, and also if they're invertible. But we'll assume that they are both square and invertible here. So in the case that these are square and invertible, this will equal phi, because we flip the order and we invert each one individually. So phi inverse theta transpose inverse. If you've seen this notation before, the inverse of the transpose and the transpose of the inverse are the same thing. So we can just write inverse transpose like that, times phi transpose times y. These two things will cancel out here. So this just equals phi inverse times y. Now, let's look at our predictions. Well, in this case, theta here will just equal phi transpose y. So this will equal phi times phi inverse times y, or it will just equal y. So our predictions equal our output. Or sorry, our predictions equal the output in our training set. That has nothing to do with actually how well our theta actually works in some sense of predicting new examples. So this example I'm showing here, the phis are just random, completely random normal examples. The y's are random. There should be no correlation between these two things. There's no way that you could predict what this is in general from this thing. For more examples, they're just random. By definition, you can't predict it. Yet, when you apply linear regression, you get 0 loss on these examples. And so what's happened here is that this is an example of overfitting, right? We have too many features. We're not actually learning anything of value. We're just trying really hard to pick some random thetas that, for whatever reason, will give us exactly the right answer on the data we have. This goes for polynomials too, by the way. As long as you have m distinct points, a polynomial of degree m minus 1 can pass through all those points exactly. So you can get 0 error. The only reason why you might not, by the way, is due to numerical rounding errors. That's the one tricky thing you have to be careful for. But you can fix that too by picking the right polynomials. So that's probably not going to be a very good function for predicting new examples. So the point of all this, though, is that we do not want to use the loss function to evaluate what is actually a good performance of the algorithm in terms of the features we have or the regularization, things like that. A better thing to do, which I've been hinting at for a long time, though now I can finally define it a little bit more formally. A better thing to do is to split the data we have up into two sets. And we'll call one a training set and one a testing set. Actually, forget about splitting for now. We just have two data sets that are somehow the same, in the same distribution. They're not the same examples, but they're the same distribution. We'll eventually get it by splitting up a single set into two different examples. But for now, we have some training examples and we have some testing examples. So like before, I'm going to let xi in Rn and yi in R. The same goes for classification, by the way, but I'll just talk about the regression case for now. These are our training set. And our testing set, they are the same dimension as this, but they are different examples. And I'll denote them xi, and I should say here I goes from 1 to m. Here xi prime is the same dimension as x, the same type of input, and yi prime the same type of output. And here I goes from 1 to m prime. We don't have to have the same number of training examples, testing examples. So what we want to do is use the training set to find our parameter theta. So we're going to find theta, and so our parameters from the training set. So just like before, theta star is going to equal the argument. That just means essentially the argument that minimizes this thing. Theta of sum from I equals 1 to m of our loss function, theta transpose phi xi, yi. Okay? And now, so that stays the same. This is what we're doing before. We're picking the theta that minimized this sum of loss functions. Maybe post-vectorization, but we won't worry about that just yet. Now, to evaluate how well we actually do, we look at the loss not on the training set, but on the testing set. So the evaluation of how well this actually is, because of course the training loss we can fit as well as we want. The actual evaluation here is going to be how well we do on the test set. So I'll write this as 1 over m prime. We'll get the average loss in the test set, say, of there should be a sum there. Right? That's incorrect. The sum from I equals 1 to m prime of the loss of theta star. So these same thetas we got from the training set, evaluated, making predictions, though, on the test set. So it's important these primes are here. And there should be a sum before this guy here. So basically, idea is really simple, right? And you probably sort of had this idea in your heads anyway, of something you should be doing. We train the system, find the parameters based upon the testing set, or sorry, based on the training set, and then we evaluate it on a different set of data. Because we want to know, in some sense, not how well is it going to work on exactly what we already know about. I mean, from a value standpoint, it isn't very good if we can tell us what we already know. We want to evaluate how well it's going to do on things it has not seen before, examples it has not encountered or did not encounter during training. Performance on this test set is also sometimes called generalization performance. So we're talking about how well this classifier or regressor generalizes to situations it has not previously, examples it has not previously seen. This is really the crux of machine learning in some sense, right? We don't care about how well we do on things we've already seen. That wouldn't be very useful. Like, that's just like a list of data, right? What we want is something that will actually perform well on things it has not seen yet, a general function that works well. Now, as I said, that sometimes there is a way to naturally, so I guess the question then is, how do you pick the training set and testing set? And sometimes there is a natural way of picking this. For example, if you're doing something like a forecasting task where you want to know, okay, what's the peak demand going to be tomorrow? Well, maybe what you'll do then is sort of train on, because you're never going to have future information, you might want to do something like build your testing set from the years 2008 to 2012, and build your training set from 2008 to 2012, and make your testing set 2013 so far. Right? That kind of makes sense because what we really care about is how well is it going to work in the future going forward from now. So we'll sort of simulate that. Well, if we've done this, starting at the beginning of the year, this is what it would have looked like. There are some cases where you have that kind of natural, you sort of have that natural choice in what training set and testing set you pick. But even more common than this is to just ignore all of that and treat all the data as if it was unordered and just, the formal term is independent and identically distributed, but don't worry about that. Just you treat it as if it's all one big batch that has no sort of ordering to it. And you just chop it up and take, say, 70% as your training set and 30% as your testing set. And importantly, take sort of random 70% and 30% as your training set and testing set. So here's MATLAB code that does that. In this example, I guess, phi will be a matrix of m, size m by k. So the first line there says, OK, I'm going to set the number of examples in my training set to be equal to 70% of m, and Ceil just rounds it up to the next integer. So we're talking about integers here. We can't talk about half an example. The next says the number of examples in my test set is going to be m total examples minus the ones in my training set. And then important, this line is the important one here. It says p equals a random permutation, rand perm, of size m. So what rand perm does is it generates a random permutation, a permutation of the numbers 1 to, in this case, m, that basically randomizes the order of numbers. So we'll return a vector of of m dimensions, where each item in that vector is an index that is between 1 and m, but is in a randomized order. And the way you use this then is you say that phi train, so I'm not going to construct a set of training examples. So phi underscore train equals phi, whereby indices of phi are these random permutations, p 1 to m train. And then all the rows, we take all the features. Similarly, you do the same thing for y. And for the testing examples, you take the training plus 1 to the end, so all the rest of the examples. And it's important to actually have this random permutation there. If you don't do this, then what you can get is you can actually become biased by whatever order your examples happen to be in. So a lot of data sets that are released, for example, for classification, say, will have all the negative examples first and all the positive examples. So if you were to leave out this p here and say this was 70%, and say you had 50% negative, 50% positive, then your testing examples would all be the positive class, say. And your training examples would be 50% or whatever it is, about 70% positive and about 70% or 30% negative. So 5 over 7 positive and 2 over 7 negative. So that will not be a good thing. So it's really important if you're going to take a random subset of your data to be the training set and test set, it's very important to randomize your data first. All right. So we are almost. Let me just show you these next graphs, and then we'll end there. So this is our regression example again. So we have our example of high temperature for the day and the peak hourly demand that we see. Remember, what we're going to do is we're going to fit a function of this of varying degrees. And so the question is, what degree, for example, what degree polynomial should we pick here? We're going to fit a polynomial function to this data. What degree should we pick? Well, here is a plot of the average squared loss, the average squared error, on the training set, on the testing set, when we are increasing the degree of the polynomial. So you remember, right, that when we plotted, a degree 1 polynomial, that was just a straight line, so that didn't look very good. Degree 2 was a little bit better, wasn't great still, and that's actually exactly what we see here. So 1 was a straight line. A straight line doesn't fit this data very well. 2 is a quadratic function that doesn't fit that great. 3, by the time there, we were getting actually pretty good fits. This cubic fit looked pretty good, and this is exactly what's sort of borne out here. So what you see is after 3, it doesn't get much better. But it, in this whole range actually does pretty well. Both on the training set and the testing set, we're getting pretty good error. So you could pick anything kind of in here. Is it maybe a good size, a good number, a good degree of polynomial to fit. And then after 8, or so, well, our training error keeps going down. As I said, by definition, it will always keep going down. It will never go up. So we'll keep doing better and better on the training set the more examples we add, but we're starting to creep up the error on the testing set. If you keep going, and as you saw, remember how crazy those functions looked when you had like a 50-degree polynomial, this kind of stuff. If you keep going, you see some very bizarre behavior here. So now this is all plot. Instead of this is a plot from degree 0 to, I guess, degree 1 to degree 10. I guess I'm not writing 10, so I guess it must be 9. But all of a sudden, if you actually go further, higher with your degree here, up to 40, say, well, you get very odd behavior indeed that you probably would not want to use those ones. So all of a sudden, your training error keeps going down. Doesn't improve by that much, by the way, but it definitely is going down here. But your testing error just gets ridiculous. I mean, there's no way you'd want to use something with that high of an error. It's much worse than just predicting a straight line, or in fact, even predicting everything to be 0 at some point. It actually gets worse than that. So let's not do that. Let's instead pick something where the training error is actually the minimum. Sorry, the testing error is actually at its minimum. And the same thing happens for radial basis functions. So as we increase the number of radial basis functions, there's some nice spot, say 4 to 10 or 4 to 12 maybe, where it looks like a very good fit. As you increase this, though, to 100, it's very, very weird, right? You probably don't want this point over here. That's not a very good fit. Also some weird behavior. I mean, this is not like it increases linearly because the randomization of the spacing, essentially, I mean, for some reason, right here is a little bit better than over there. But you really shouldn't be picking any point out here. They're all still worse than these good points here. So don't pick these points out here. Pick a reasonable number down here. And the last thing, I'm sure the same thing for a value of the regularization parameter. So if we regularize our weights for, I think I'm going to pick 70 radial basis functions. So I'm going to pick 70 radial basis functions, so it's up here. This is showing it with no regularization, so lambda equals 0. And here's what this looks like. So this is actually a very cool plot here. Because A, it's smooth, which is really nice, much smoother than the other one. So lambda, unlike other ones, seems to have some sort of smoothness, which you kind of understand, because that's sort of a real value thing, whereas the other ones were kind of discrete valued. You're increasing it, so there's some randomization. Lambda here, when lambda equals essentially 0, that's the case we saw on the slide before. Training error is very low, and testing error is very high, because we're not penalizing big weights. We're not penalizing weights on our theta parameters. As we increase regularization, there is a point where the training error and testing error actually start to meet up. What's happening here is that we are penalizing the weights enough that acts as another form of kind of restricting the class of functions we have. And that actually will also decrease error on the testing set. As we make lambda even bigger, what will happen is now we're penalizing it a lot. We're penalizing it so much that lambda, the solution we get is actually going to, theta, the solution we get is actually going to be 0. And so up there, our training error and testing error might be actually very close because they're both really high. Essentially, they are when you use theta equal to 0. So this curve here, and maybe I'll mention it again starting the class next time, but this curve here is the same thing you see training error versus testing error when you vary values of this regularization parameter lambda. So we'll finish up with that today. Again, I have office hours today from 2 to 3 in my office, which is gate 7115, and hope to see people there. I'll hold them again I'll be there probably on Wednesday if you'll want to stop by too. I just have to be there all the time, but then I'll hold them again on Friday as well for people that want a few days before coming in. All right.